Section 12.4, we're going to take a look at similar triangles and other similar figures. To start with, we're going to look at what we're talking about for triangles. Triangle ABC is similar to triangle DEF. You'll notice there's a tilde between them. If and only if all the angles, or pairs of angles I should say, are congruent. So A and D are congruent, B and E are congruent, C and F are congruent. And the ratio of their sides is the same. So that's what that last piece is showing you, is it's three ratios, and the ratios are all the same. In words, triangles are similar if and only if their corresponding angles are congruent and there is a common ratio, or it's sometimes called a scale factor, among corresponding side lengths. You encounter similar figures all the time. If you use a copier and you increase or decrease the size, some of you may have that opportunity for the future. If you have a student in your class who needs an increased size because they have vision issues. When I project through the projector, my screen here is exactly the same, proportionally speaking, as the screen you see. Okay, that's a scale factor. All of everything's the same. It's a similar figure. It's just larger, the one that projects. And we talked about it for triangles, but it's true for all polygons. Similar polygons are any two polygons with corresponding interior angles congruent. And again, the common ratio called the scale factor among corresponding side lengths. Now, there are three ways to prove similarity of triangles. We had more than that for congruence of triangles. How many did we have for congruence of triangles? In my mind, I'm thinking it's 5. It may have just been 4. So we don't have as many different ways with this, but we also don't have to prove near as much. The first one's called the side-side similarity. If corresponding sides of two triangles are proportional, then the triangles are similar. So we can see in this one, even if I didn't have everything marked quite as neatly as this is, if you look at this corresponding ratio, 4:2, and this is 6:3, that's the same ratio. Sort of the tall pieces on the top are twice as long as the base. Okay? So if the common ratio exists, then we're good to go. I think the picture I have on your paper might be different than this one, is it? No? Okay, I changed my pictures at some point then. Fantastic. Side angle side. Well, that should sound familiar because we've had one of those for congruence. If two sides of two triangles are proportional and the included angles are congruent, then the triangles are similar. So again, what you'll notice here is that this is a 4:3, and that's the same as an 8:6. And when I say that, maybe I should write one of them out. I apologize. What I'm saying is that 4:3 is equal to 8:6, like this. If I were to take 8/6 and I were to reduce the fraction, it would reduce to the same value as 4/3. And then we have to have a congruent angle as well. So the ones that are marked here are angle B and angle D on this one. They happen to be 90-degree angles. Wouldn't have to be, but they are on this diagram. And our last one, I'm sure it's the last one, yeah, is angle-angle. If two angles of a triangle are congruent to two angles of a second triangle, then the triangles are similar. Why do I not really need all three angles? Why is two angles enough? Okay, let's make up some numbers to let you think about it a little longer. Okay, say that louder, Allison. All three angles in there have to equal 180 degrees. So if I know that this one is 50 and this one is 40, and this one is 50, and this one is 40, the last two have to add up to, I mean, it all has to add up to 180, so the last two have to be equal as well. So I really don't need all three of them. Having two of them forces all three of them. Some properties of proportions. If a line parallel to one of the sides of a triangle intersects the other side, then it will divide the triangle into proportional segments. So picture-wise, what we are suggesting is that this line, oh, that was terrible. This line and this line are parallel, okay? It's a parallel line to a parallel line segment. Then what that means is that the ratio of x to y on, hang on, let me write it the way that they actually say it. It divides as, yeah, I was ready, right? X over y is equal to z over w. There's lots of parallel or similar statements I could write down, but that's the one that we reference right there. Okay? The second one is that if the line divides the side of triangles into proportional segments, then the line is parallel. You've seen that happen before. You've seen a statement where we're able to reverse it, and it actually works as well. It doesn't work for every statement, right? If I were to come into you, and I think I maybe said this last time, or maybe I said it in my other class, and I were to say to you, because I am a mom, therefore I'm a woman, you would shake your head and say yes. But if I said, because I'm a woman, therefore I'm a mom, you would say, well, maybe not. It doesn't work both ways, right? This one does. So if I have that x over y is equal to z over w, then I know they're parallel. Or if I know they're parallel, then I have that corresponding ratio. So that's the second half of this. And this is an interesting one because it actually is telling you now that there's really nothing special about drawing one parallel line in. I could draw lots of parallel lines in and things would be very similar. So if parallel lines happen to cut off congruent segments on one side, then they cut off congruent segments on the other side as well. And that's kind of cool because basically it's saying that if A equals B equals C equals D, then that means, if they're all parallel, that E equals F equals G equals H. Doesn't mean that A and E are the same. But it means that all of these are equal to each other, and all of these pieces are also equal to each other.
Does that go for the same, like, the example before?
Yes. These just don't necessarily have to be equal. They could be proportional only.
Okay.
Like, for instance, this isn't drawn in such a way to be convincing of this, but like if this was 2 and this is 1.5, then over here, and this one was, I should have chosen numbers that were nicer, 4 and 3, that it would work. So this ratio has to create the same ratio over here. But over here, we're actually, the ratio that's been created is a 1-to-1 ratio. They're exactly equal. All right. I have a construction for you, and I apologize in advance because I forgot to bring my construction pieces. So try to take notes. If you don't have your compass and straight edge, which they're part of the requirements for this course, and you need them for outside of class, so I encourage you to get one. But if you don't have one, just try to follow along while I do this example. All right, so I believe if you go and watch the video that's actually posted for this one, video number 13, and I think it's only, no, this is not one. It's just video 13. I think it constructs them into 5 equal segments, but the process is exactly the same. No difference at all, but you can watch them create 5 congruent segments. All right, a mid-segment. A mid-segment is a segment of a triangle connecting the midpoints of the 2 sides of the triangle. So a couple facts about a mid-segment. The first one is that it's parallel to the third side. So in my picture, what I'm saying is that this line and this line are parallel. Okay? The second feature, which is a pretty interesting one, is that it's half the length of the third side. So let me talk just for a second about why that would be the case. So it's cutting the sides in half, right? So like this side and this side are, I mean, not side, but this side on the left, A, B, is split into two pieces that are equal lengths, right? M is the midpoint. And the same thing on the right-hand side. So what we really have here is we have this triangle at the top and this triangle on the outside. And what can you tell me about those two triangles? They're similar. The smaller one is half the sides, or have to be half as long. Now, I haven't really justified that MN is half as long, but we have it marked on the outside parts, right? This piece right here is only one of this piece right here, and they're equal, so it's half as long. Side BM is half as long as side BA, right? This is cut in half. And this is also cut in half. So when we cut them both in half, and we connect those points, we create a mid-segment which creates parallel lines, and it creates the ratio ends up being the same down here. So this is, if this is 5, then this one would be 2.5, right? It's half as long. If a line bisects one side of a triangle and is parallel to the second side, then the triangles are similar. So again, we actually established the fact that we created these similar triangles because the lines were parallel, right? And we had these other features. Well, if we have the parallel and we have the bisecting parts as well, then we also get that the triangles are similar. Again, another one of those reverse arguments that actually works. All right, another center of a triangle is what they're usually called. We had an incenter and we had a circumcenter. You guys remember those, right? Incenter and circumcenter. A third center of a triangle is called a median. A median is a segment of a triangle connecting a vertex. Centroid is the word I wanted, but it's created by a median. A median is a segment of a triangle connecting the vertex to the midpoint of the opposite side. There are 3 medians because there are 3 vertices, 3 possible other sides. And they all intersect at one point. So just like the circumcenter intersected all at one point, right? It was 3 intersection values. Same thing with the incenter. So is the medians. The 3 medians intersect at the central point called the centroid. Centroid is also sometimes called center of gravity of the triangle. Think balancing point. So has anybody seen National Treasure 2? Okay. There's a point in the movie, sometimes I'll show it in class, we don't have time for that, but there's a point in the movie where they actually land upon, it's not a triangle, it's actually a square. It's square shaped, and they're trying to balance on top of it. And so this balancing point is the idea. If you've actually got it placed correctly, you should be able to take this triangle, in a 3-dimensional sense, but this triangle, and put it upon that one point, the centroid, and it would balance. And that'd be pretty cool to watch, right? It would. But that's actually what this is. The centroid divides each median into the ratio 1 to 2. So let me show one of them on here. So if this is 4, then that one would be 2. And if this is 2, then this one would be 1, and so forth. It's a 2 to 1 ratio. The side coming from the vertex is double the length of the side that actually connects to the side. All right, we have one more example to do. We're going to do the example. Whoops, it's supposed to be an eraser. Of how to use similar triangles in a real scenario, an actual example. We're going to find the height of a tree. So there's really nothing written in here about this, but we're going to talk through what we actually have. Do you see the little girl there? Or the woman? She may not be that little, I'm not sure. I don't measure my height in centimeters. I'm not sure how much 150 centimeters is, but that's her height. She's 150 centimeters tall. I actually think she's got to be a woman. She can't be a little girl. Yeah. We'll look more at measurements and metrics some other time. We actually will. I'm not just making that up. It's another unit. It's chapter 14. Okay. So we've got a young lady. She's 150 centimeters tall. And we know that she is 3 meters away. Whoops, try it again. 3 meters away from this particular point, which is the edge of the shadow. the edge of her shadow. That's what they're trying to draw in down here with this little kind of dark piece. And it's the edge of the tree shadow. So if you imagined doing this and you really want to know how tall is that tree over there that I think I might want to climb, what you would do is you would walk towards the shadow until the end of your shadow met up with the end of the tree shadow. Like you could really do this as an experiment, okay? And she measured it. It's 3 meters. She can also measure how far back it would be to go back to the tree herself, and that's 15 meters over here. And using those 3 pieces of information, she can find the height of the tree. Now, the reason she can do that is because there are similar triangles created. Okay? I know that the angle down there at the bottom, right here, is the same angle for both triangles. And I know that we have a proportional side length. This side is proportional to the whole triangle side. Or likewise, we could talk about this, I said it wrong, this little triangle side is proportional to the whole triangle side. There is one other thing to be aware of. Do you notice that the units don't match? We need the units to match to make this work. So we need to either to decide we're going to use meters or we're going to use centimeters. Either way is okay. I'm inclined usually to use centimeters because it will mean that I don't have to deal with decimals. But I think in this case it might be more practical to use meters because if I talk about how tall the tree is, at some point I want to know how many meters tall it is. Does that make sense? So let's go with meters, all right? So if I were to take 150 centimeters, and again, I know we're going to talk about this more later, but do you know how to turn that into meters? Does anybody remember? Google, is that what you just said? It is. Good memory. All right, so 100 centimeters is equal to 1 meter. So what would that mean I need to do? It's 1.5 meters. You're right. One of the ways to think about it is that I'm moving my decimal 2 to the left. We'll look more at these ideas later. But yeah, this is 1.5 meters. So the young lady is 1.5 meters tall. Now that actually is probably a better visual for you than 150 centimeters. I know it is for me because I kind of have an idea about how tall a meter stick is. And so she's 1.5 meters tall. That's why I said she's not a child. I mean, she could be a tall child, I suppose, but you know what I mean. Okay, so we have the little triangle on the left, which is her height, which is 1.5 meters, divided by how far she is away from the end of the shadow, which was what? 3 meters, exactly. And that ratio has to be what happens for the tree. Now you need to be careful. The height of the tree is what I want, so this is H on top. I've got, did they call it H? We didn't call it anything. Here, let's call this H. So the height is on top, and at the end, or on the bottom, I'm actually measuring the length of what? Of the shadow, yeah, of the shadow. And that actually means the length of everything at the bottom. So how far away is the tree base from the end of the tree shadow?
18.
It's actually 18. So really common mistake to use 15 there. Be careful, it is 18. You can leave the M's off while you're calculating if you want. The ending answer needs them in there. How would we solve this? How could we solve this? Could cross multiply. You could also just multiply the 18 to the other side if you prefer. So if I cross multiply, that's what you guys said, so that's what I'm going to do. I have 3h meters. And then what is 18 times 1.5? $18 times 1.5. What is it? 27? Is that right?
Yeah.
It is. You're right. You're good. 27. Okay, then what would I do? Math in your head is always good stuff. And then I divide by 3. You got it? So what is my height? 9 what? Meters. 9 meters tall. Now, if you answered 900 centimeters, would it be okay? Yeah, it'd be fine. It's no problem. Be perfectly okay with me. It's another way to measure it. Any questions on that?